Hello, this is the continuation of our previous video about robot pets, and now we are going to have trajectories that depend on time. In our previous video, we learned that we can have a path in the configuration space, and now let me start with an example. For example, this is what we will have in a Formula 1 track, and we will have a car that starts with the velocity 0 around here. The mission of the car is just going around the circuit one or multiple times. In this case, we will assume that it is only once. In this configuration, we have something that is called a path. That is just the curve in the configuration space. And now what we are going to integrate in this type of configuration is the time. For example, in Formula 1 and in normal vehicles, it is easier to go straight than going through the curves, right? Because applying angular velocities have some implications that you usually need to slow down in order to go through that. So in this scenario, we'll have these two curves, and the velocity should go down and should go up during the straight lines. And when you are approaching to the curve, you should slow down again. Okay, and finally, we want to finish in with velocity 0. So the second concept that we have here is a trajectory. That is basically what we are going to define is a moving point on a path. And that task will involve time. In our previous video, we learned that one way to represent the path in the configuration space is defining a function theta that maps a variable between 0 and 1 to a configuration space, and the variable that maps that value is called s, right? When we have for different theta s, we can have a theta s that connects 2 points in a straight line, but we can define different types of paths like an ellipse or just a sinusoidal path. Now, since we want to incorporate time, what we change is that now s is not just a value that changes. Now s is a function that depends on time. That value goes from 0 to the total duration of the trajectory, and it will map to the original values that were between 0 to 1. And this is the variable that we will call t for time. If we want to study how the function theta changes on time, we will need to compute the derivative with respect to time. And for that, we will just apply the chain rule. That can also be represented in Newton notation as d theta ds times s dot. We can also study how the velocity changes, and in this case we will have the second derivative. Which can be obtained by applying derivation to the product that we got before. And this will be the result in the Newton notation. For studying complex trajectories, we are going to start with the simplest one, that is just a line, and the robot needs to move through that line. For that, we will integrate the path with time, and that's what we call time scaling. Let's study how the velocity in S changes with time. One way to do this is called the trapezoidal profile, where we apply a constant acceleration, and then when we reach a desired velocity, we keep that velocity until a point where we need to decelerate. However, that trapezoidal profile requires a drastic change in the acceleration. There are other options, like a smooth path that can be computed by a polynomial curve. And finally, there is another type of curve that involves generating the maximum acceleration but in a smooth way, that is called the S-curve. In this video, we are going to study the trapezoidal and the polynomial. The S-curve can be studied from the book. For the trapezoidal, as we said before, we applied an acceleration A. In some cases, we can do this when we want to apply the maximum acceleration, so we want to reach our final destination as soon as possible. For that, what we need to do is we need to separate our trapezoidal function in three parts. The initial part, where we accelerate; the second part, when we decelerate, we maintain constant velocity; and a third part when we apply a negative acceleration. For our first part, what we have is a set of equations that describe that the acceleration is equals to a, the velocity is equals to at, and the position is just the integration of the previous one and will be equals to at squared, right? That's on a straight line that goes from 0, 0 to a desired velocity. In our second part of the function, what we have is that we stop accelerating, so the acceleration is 0. We maintain a constant velocity, and the position with respect to time will be equals to Vt minus over 2a, just by solving the equations, because we start in Ta. And finally, when we stop accelerating, when we stop maintaining the constant velocity and we start to decrease the acceleration, we will have that the acceleration is equals to minus a. The velocity now describes a line that depends on the initial acceleration, and also the time, that the duration of the whole trajectory, and we will have that the final position can be described by integrating the previous equation, taking into account that we are integrating from t minus ta to t. The problem of the trapezoidal profile is that the acceleration has to change very fast. We change from 0 acceleration to a, and then to a to 0 again to maintain the constant velocity, and then we need to change to minus a, and that's a very drastic change. There are other ways to solve this problem, and one way is to define a polynomial that describes a small curve like the one that is depicted in the figure. We just define a 3-degree polynomial that will be sufficient to capture the initial position and the initial velocity. There are other cases where we can have a higher degrees polynomials, like a 5-degree polynomial, in case we want to consider initial acceleration and the fourth derivative of the position. In this case, we have the polynomial and initial conditions. The initial conditions depend on the point where we start, which is time equals to 0, and we will have that the initial position is equals to 0 and the initial velocity is also equals to 0. The other case and the other condition is in the end, when we have that t equals to t, to big T, that is the duration of the trajectory, and the final position of the trajectory is equals to 1 and the velocity is equals to 0. We want the robot to stop when it ends the trajectory, right? We can see that in the curve on the left that the peak in the velocity will depend on the inverse of the duration of the trajectory. That's why if we want to flatten or to make this curve smaller, like something like this, we just need to increase the duration of the time. Okay, so we have a system where we have four constraints, four parameters that we need to obtain, and we have 4 constraints. And solving this system, we can obtain the parameters. The result is that A0 is equals to 0, A1 is equals to 0, A3 is equals to 3 over the duration of the square of the duration of the trajectory, and A4 is equals to 2 over the cube of the duration of the trajectory. This will give us a smooth trajectory that we can easily follow with a car. Let's continue with the example of a straight line that goes from point A to point B in a straight line. In this case, we want to give some values to have an idea about how the function s changes. In this case, the values will be 10 meters for the distance between A and B, and we want to complete that trajectory in 30 seconds. The equation of a line that follows in the x coordinate will be equals to the straight line, that is s equals to x, the point in B, minus the point in A, plus xa. We know that we are in a single dimension because if we draw the axis, we will have x, y, and z z and y will be 0, so we only need to study the point in x. Based on our values, we can say that xa is equals to 0 and xb is equals to 10. So the result is a line that changes as a function 10s. Now we need to study the function s. For that, what we learned before is that we can describe this function by a polynomial. and this polynomial can be processed using some initial conditions to obtain the unknown parameters. Those conditions are that the position starts in 0, the velocity starts in 0, the final position of s is equals to 1, and the final velocity is equals to 0. Okay, we will stop in B. And applying the equations of the previous slide, we get that A0 is equals to 0, A1 is equals to 0, A2 is equals to 3 over t squared, and t in this case is 30 seconds, so it will be 3 over 900, which is equals to 1 over 300. And we can obtain the final parameter that is equals to 2 over t cubed, and this is equals to 2 over the cube of 30 seconds, and it will be equals to 1 over 1350. As a result, we have our desired function s, and we just need to plug a 0, 1, 2, 3 into our polynomial, and we will have that st is equals to t squared over 300 plus t cubed over 1350, and this is the function that will describe how the robot moves in the s parameter. If we want to describe x in terms of time, how it changes based on time, we just need to plug s into the previous equation. There are multiple ways to compute trajectories. The first case that we study is where we define a path that is just a function that depends on s, and it will be a curve in the configuration space. And based on that path, we can define a time scaling, and we will find how that function, that s changes with time. And we saw that we can see that behavior by studying how the time changes with the velocity. Another way to do this is by defining waypoints. In this case, we just defined the locations where we plan to go through, the velocity at that point, and we will find a line that passes through those points with the velocity that we want. In that case, what we are going to do is finding directly the function theta, but it directly depends on t, and our work will be in finding that function. This is our next video.